Are there any questions? Anybody have any questions? Really? Oh, you know what? Something's been going on with YouTube lately. That when I upload my videos, they are, it used to just automatically put them out there. Now it's making them private. And I have to go in and switch it to public. Yeah, see, that just started like last week, and I'm not used to it yet, so I need to. So I'll update it. Okay, well, what were we doing last time? Systems of linear equations, right? Elimination, right? hey, easy. So if we have a system of two equations with two unknowns, we see that there are two approaches to solving it. And today what we're going to do is we're going to extend this now to three equations and three unknowns and see how we go about doing it. And then I'm going to see how many of you have calculators that are decent. So whoever has a calculator, let me just make sure, break out your calculator. Let's see how many of you have a fancy enough one to do it. Let's see, that's what you got. Okay, I don't think that's enough of you. Because there's a real easy way to do it on your calculator to solve these systems of equations. It's just a matter of typing it in and it splits out. Well, like that, yours, I believe yours actually does, but it's a little complicated. I haven't used one of those in a while. That does it, that does it. That does it, yeah. If you have a fancy graphing one, if you have one, bring it. Don't go buy one. But if you have one, bring it, and I'll show you how to do it. I'll show you in class today how to do it, and then next class we'll get some more practice with it, okay? All right, so last class I ended on note, well, we did a group quiz, example 12.1.6. I'm going to go make this 12.1.7. Okay, I'm going to give you a system of equations, and let's see if we can solve it. Okay, how many equations do you see here? The instructions here are to solve. You see three equations, right? So what we have are three equations, three variables, right? Every single equation that you see here is linear, isn't it? Linear equations have equal signs, they have variables, the highest power is a 1, or all the powers are 1s on these variables. And I'm going to point out something somewhat interesting that's going to be useful to us in a minute. Notice that the first equation has x, y, and z in it. The second equation has only y and z in it. And the third equation just has z, right? Okay? Now, that means that below the x, there's nothing here, right? Below this y, there's nothing. So it's almost like there's this like blank triangle in here. Do you see that? It's like a diagonal. You'll kind of see it. It's okay. In fact, if I wanted to, I could say that there's really like nothing here, and then nothing plus the z. Couldn't I say that? Now, right now, it's not going to seem obvious why we would want that. But let's just remember that if we ever have something that looks like this, where we've got this like diagonal x, y, z, and everything below here is blanked out, let's see how easy it is to solve this, all right? So let's see, how would we solve this? Do we know any of the variables right now, what they are? I know z is 2, don't I? From that, I can go to the The second equation, put equation 2. That's the second row, right? This one. And this one has just y and z in it, but I know what z is. So I can solve for y. So I can write x plus 2z equals 5, but z we just said was what? 2. So I could say y plus 2 times 2 equals 5. 2 times 2 is 4, so subtract 4 from both sides, then y is what? 1. So now I know what two of the variables are, right? I know what z is and y. Now I go to equation 1 that has x, y, and z in it. I know what y is. I know what z is. I should be able to find x. So now going into equation 1, x plus y plus z is 10. We get x plus y we said was 1 plus z was given to us as 2 equals 10. So x plus 3 is 10, which means x equals 7. So I found what all the variables were, right? And so remember how we did ordered pairs for our answer? Here we do what's called an ordered triple. An ordered triple looks like this: x, then y, then z in parentheses. So for this, we'll have 7, 1, 2. All right? Now, does anyone remember from last class that when we had two equations and two variables, that really it represented the intersection of two lines? Okay? And do you remember I told you that when you have three equations and three variables, it's three-dimensional, right? Each one of these was a what? A plane, right? A plane? So when you have three equations and three unknowns, what you're trying to do is figure out where three planes intersect each other. So I'll give you an example right here in this room. I don't know where my ruler went. Oh, there it is. This wall is a plane, right? The ceiling is a plane, and that wall over there is a plane. They all hit each other where? Top corner over there, right? This top corner of the room is the point at which this plane, and this plane hit each other. Yes? That number in three-dimensional space would represent that point, okay? Now, we know with lines you can only have three possibilities, right? With lines, you could have them hit each other at one point. You could have them never hit each other, right? Or you could have the same line, they hit each other everywhere, right? That's what we had with lines. But with planes, what could happen? I mean, you obviously can have one point, right? But what else could you have? Could you ever have that they never hit each other? Just think about, like, you know, this building, this floor level, right, is one plane. This ceiling is another plane. And the ceiling of the second floor is the third plane. Three planes, they're parallel, so they wouldn't hit each other, right? Does that kind of make sense? And then you could have, how about a situation like this? This is going to be hard to do, but how about this is a plane, right? This right here, say, is a plane, and this is a plane. Do these planes hit each other? They're hitting each other right here in the book, right? Right in the crease of the book. But are they hitting at a single point? They're hitting actually along the entire edge of this, which would be a line. So you could have planes intersect at a point, never intersect, or intersect at an actual entire line. Yes? Usually, if you're trying to understand the fourth dimension, you think of time as the fourth dimension. So, like, you know how you have x, y, z is like a position? Then you would have a fourth one. X, y, z gives you where you are, and then t would be when you were there. So, like, let's say right now I'm standing at a point in three-dimensional space. Let's just say it's 3, 2, 5, and then let's just say I'm going to look at it's 11, 12, right? Okay, so now if, oops, sorry. Forgot to silence that. So now if I move my position, right, the 3, 2, 5 is going to change, yes? But I'm actually, now I'm talking to you, it's a different point. It's actually 11, 13 now. That's a totally different point than what it was just a minute ago, right? You see what I'm saying? So you can look at that fourth dimension as like a clock running in the background. That's the way most people visualize, or not visualize, but try and understand the fourth dimension. Now you want to go 5 dimensions, we're going to start having problems, right? There's actually, you can have n dimensions, n can be any number, and you can actually have an infinite dimensional space. So a space that doesn't have any restriction on, it's just infinitely dimensional. That's what a math person would get into later. All right, so do you agree that if this thing was kind of like diagonalized like this, it was relatively easy to solve? I just figured out, well, z is this, go back, you find y, go back, find x, yes? All right, as you might expect, that's not the way they'll be presented to you, right? So our goal is going to be to get it to look like this, because once it's there, it's pretty simple. Understand? Okay, so let's start with an example that we hopefully can get through. Won't be too painful. All right, let's try this. Okay, that one looks good. 12, 1, 8, I think. Yep. Solve this system. Is everybody ready for summer? Or just this semester to be over? Yeah. There you go. Now, what were the things that we could do to a system of equations? You can always add anything you want to both sides of an equation. You can always multiply both sides of an equation by something. And the big one was you can always add two equations together, right? That equation that you get when you add them together can replace any of these, right? That's what we did last class. So my goal right now is to try and get nothing to be here and here. I'm going to try and eliminate, I'm going to try to eliminate these two, get them out of there, okay? And after I do that, then I'm going to try and get this out of here. Because if I can do that, I will have that little diagonal thing that I was talking about, right? Agreed? Okay, so let's first start with, what was that last one, 8? Let's first start by trying to eliminate this x right here. How can I get this x to go away? Well, I'm gonna leave the first row alone. Okay. In other words, that's the one I'm going to keep the whole time. All right. That's the one at the end when it's a diagonal. That's the one I want to still be there. So I'm going to go ahead and multiply the second equation by -3. Now, by doing this, I'm going to make a -3x here, right? And then when I add it to the first row, that's going to go away, isn't it? Okay, so I'm going to first transform this system. Get used to rewriting the system over and over and over, because that's what you're going to have to do. So -3x, positive 9y, minus 3z equals -30. So just make sure that that -3 passes through everything, right? And then the last equation, just leave it alone. I'm not touching that. I just said, just get used to rewriting everything. Don't ask me, do I have to rewrite it? Just do it, all right? That's the standard practice here. Now, I'm allowed to add any two rows together, or any two equations, which I'm going to start calling rows, and that answer can replace any row I want. So I'm going to take these two rows and add them together because I know that will make the x go away. And so I'm going to rewrite this system. My second row is what I'm going to replace. So watch the way I write this. This is going to be row 1 plus row 2. I'm just letting you know right here what the second row in here is going to be what I get when I add these two together. So go ahead and add them together. You get what? 0, so I'm not going to write anything. How many y's? 12 y's? Right? That was 3y plus 9y. How many z's? -1z or just -z equals the number? -26. Make sense? Now, the other two rows I'm going to need to write down also. Yes? So how about just writing this first one back the way it was? 3x plus 3y plus 2z equals 4. And the last one, 5x minus 2y minus 3z equals 8. So I'm on my way, right? I mean, I've got this thing cleared out. Yes? I added row 1 and 2. So when you add two rows together, whatever you get as your answer can replace any single row you want. You get to choose. Okay? That answer can replace it. The other rows stay the same. You don't change those. Okay? That's the kind of thing about Gaussian elimination, or elimination. I remember I told you the guy's name Gauss, right? But that's the thing about it, is that you are allowed to do that. So what should I try and clear out now? Not the y's yet. Remember what we're going for here, right? Let's clear this x out now, okay? We're going to get all the x's gone first. So I want to make this 5x go away. And I have to work with the first row up here. So how am I going to make the 5x go away with the 3x? 5 on top. You want to multiply the top by 5? That's fine. But then you're going to have to multiply the bottom by what? -3. Right? That'll create a 15x on the top row. It'll create a -15x on the bottom row. And then when I add them, it'll cancel. So I get to rewrite this thing. Be careful here. 15x plus 15y plus 10z equals 20. What do I do with the second row? Nothing. I'm not messing with it, right? Because I already have it where I want it, right? I have the second row has just y and z in it, and that's what I wanted. Okay, so now my last row here is going to be -15x plus 6y plus 9z equals -24. We all okay with this? Okay, all I did there was multiply through. Now what I'm going to do is I'm going to rewrite the system again, but I will be replacing which row with what? The bottom row with my row 1 from up here added to my row 3. Does that make sense, the notation I'm using here? This third row is going to be the result of adding row 1 and row 3 together up here. So let's do that. Let's add these, and we'll come back and fill everything else back in. When I add the 15x and -15x, I get 0, right? 15y and 6y is 21y. 10z and 9z is 19z. And then 20 and negative 24 is negative 4. And notice when I'm doing that, I'm totally ignoring the second row, right? I'm not adding all of them down, just the first and third. Okay, is that all right? All right, I'm going to go back and replace the second row with exactly what it was because I did not want to touch that row, did I? And then what about the first row? Same. What do you mean, same thing? What should I use? I can use 15x. I can use this, right? Or I can go back to the original, which would mean all I'm doing is I'm deciding to take this row right now. I realize I made it more complicated by multiplying by 5. So I'm going to undo that by dividing by 5, just to make my numbers smaller. Make sense? So I'm going to put here divide by 5. Okay, that's what I'm doing here to get my first row back to its original form, 3x plus 3y plus 2z equals 4. We good? Nope. You're free to do. I didn't even have to do that. I could have left it as 15x plus 15y plus 10z equals 20. It's just bigger numbers, so I'm just trying to make things a little bit easier to work with. Any questions? We're almost there, right? Remember, we're trying to get a 0 now, 0 here, and then a 0 here. So what? These two, right? To make the y's go away, why don't I just mess with these two equations? Right? Just these two. Ooh. How am I going to make these go away? You could. You could. Well, but what's going to happen is if we do that and we take this and add it to this, the y's are going to go away, but we're going to make an x up here. And so then we'll have a problem. So you want to work with just these two. I know it looks bad, but I mean, you have to think of a number that is a multiple of both 12 and 21. And if you can't think of something that's a multiple of both, you can always use these numbers. Like I can use 21 here and 12 here, couldn't I? It's going to be big numbers, but, or make one of them negative. But is there, what are the multiples of 12? Well, I don't want to make fractions out of this. Okay, 12, 24, 36, 48. Yeah. Yeah, so look, I mean, you might be able to get something, but I think what I'm going to do is I'm just going to go 21 here, and let's go negative 12 here. So we could use 84? Yeah. So how many of you think you would find 84 on your own and you want to go with 84, yes? Or do you want to just do the 12 and negative 12 and 21? So let's take a vote. Should we use the fact that, what is it, 84? Right? It's all going to cancel. It's just a matter of how big the numbers are. This will always work. If you can't come up with a number, you can always use just, if you want to make the 12 go away, use this number up here, and then use the other number down here to make sure they're opposite in signs. This, well, I'm making this 21 so that when these multiply, it's positive, right? And I'm using negative 12 here so that when these multiply, it's negative. But I could have done negative 21, positive 12. I'm going to stick with this just because I want you to see, you know, this is like the fail-safe method that'll work. Okay, so here we go. My new system is my top row doesn't change. All right, 21 times 12, right, is what I need to do. That's 252. So 252y minus 21z equals 26 times 21, but negative, so negative 546. You understand what I'm doing, right? 21 just got distributed through to everything here. Now I distribute negative 12 through. So I should get a negative 252y. And then negative 12 times 19 is negative 228z equals 48. positive? Now what? That's right. I'm now going to rewrite the system. I'm going to replace the third row with what? The second one and the third one added together. So add these two straight down now, and what do we get? So these go away. What's negative 21z? What is it? Negative 239? 249. Negative 249z equals, careful, 39, negative 498. Right? Now I have to put the other rows back in. So I need to replace the second row, right? Or put the second row in. I could put this second row in, couldn't I? Or I could go back to the original second row right here. Yes. Yeah, but I'm going to fill everything back in first. So is it all right if I come back and replace it with this one? So 12y minus z equals negative 26. And then my first row, I'm going to leave it alone. I get this. All right, I have reached my goal, which was to get nothing here, nothing here, and nothing here. I get this diagonal looking thing underneath. And if I get that, I should be able to solve for all the variables. So let's get z over here. Looking at equation 3, or row 3, I have negative 249z equals negative 498. Divide both sides by negative 249, you get z is what? 2. Oh, how convenient. Understand? Now I go to equation 2, or row 2, which is 12y minus z equals negative 26. I replace what? Z with 2. And that gives me 12y equals what? Negative 24, because I add 2 to both sides. And that means y is negative 2. Oh, man. This is great. No fractions. And then to get the last one, I go to equation 1. I'm out of space. Whoa. So here's my equation 3, which now is 3x plus 3 times y was negative 2, and then plus 2 times z, which was positive 2, equals 4. Let's do our multiplication first. Negative 6 plus 4 equals 4. 3x minus 2 equals 4. 3x equals 6. X equals 2. Now the answer is an ordered triple. 2, negative 2, 2. All right? A lot of you have to take pre-cal. One of the first topics that you cover in pre-cal is a topic called partial fraction decomposition. And it's usually that kind of like you get in that class, it's kind of like, what just happened, right? I mean, it's that kind of like slap in the face, like, whoa, what did I get myself into here? What? Partial fraction decomposition. What it is it's a reverse process of something you know how to do already, which is add two fractions together. And when you add two fractions together, you get a common denominator and you put them together. It's the reverse process of that. It's taking them apart, which is much more challenging. So to do it, it actually turns out that you need to be able to solve a system of equations. All right? I might give you a sneak peek at that, because that way it won't be completely that slap in the face in pre-cal. So this is a very, very useful thing as you move on. Now, partial fraction decomposition is something that you need in calculus too. So it's kind of like just keeps building on itself. So let me show you now how our calculator could have got the same result. All right? Yes? Because I think it's worth it. Not in this class, because on your test, I'm going to ask you to do this problem by hand and get the answer. But you can check your answer with your calculator. All right? And when you're in a class like Cal 2, they get to a point where in Cal 2, you get to this right here. And at that point, the teacher just writes down 2, negative 2, 2, and keeps going. Doesn't show any of the work for it, and expects you to be able to get that on your own. So usually it's just a matter of, okay, I have my calculator, I'll just do it on my calculator. All right? So I think it's worth it. If you're going to Cal 2, I definitely recommend you get a graphing calculator, because you'll find it useful at some point. So with the calculator, 12.1.9, using calculator to solve that same system. All right, now the instructions I'm going to give you are specific for TI, Texas Instrument, TI 83s, and up. So most of your calculators, if you have a Texas Instruments, this will work. How many of you have a TI graphing calculator? Right? We'll have to look at that one. I don't know if that's going to do it. So if you have it, bring it next class, but I'm still going to show the instructions here, okay? So every calculator is a little different. If you have the 84, the 84 Plus, or the Titanium 89, depending on your calculator, the way you do this is a little different. But I'm going to show you the way that's kind of universal to all of the TIs. What we need to do is we need to bring up an operation. We need to find a function in your calculator called RREF. Okay? Now, the way you get to this is usually hitting your menu, or trying to get to what's called your matrix menu. So I'm going to go around, I'm going to help you find this on yours. Yours is going to be, you have a matrix menu, see it under the map, the blue? Okay, bring that up, then go to math, and scroll down till you get to RREF. Okay, now write down what you just did, or do it again until you understand. Okay, that's good. Then you'll have to, next class, well, he's got his. Did you find RREF? Perfect. Just leave it right there. Okay, you'll bring it. See, yours is under, you have a matrix menu, that blue one, so you have to hit blue matrix. Now go to math. Scroll down till you see RREF. You found yours? Let me see. This one, I don't know. I'd have to look into the manual on this one. This one has a cheat sheet on the back, right? Yeah. I don't know right offhand with this one. Okay. I'm not saying go get a calculator. Do y'all have one or no? Yeah. You have a kind of fancy one? Okay. So just for now, if you do not have your calculator with you, but you have one, just write down what I've got here. You need to go home and find RREF. When you find it, go ahead and select it, and it should bring you to a screen. Your screen should be blank, or not blinking or whatever. Should have RREF, and it should have a parenthesis like this. Has everyone got that? Okay. Yes, you're there. Now, what this stands for, not that it's really important, is what's called reduced row echelon form. What that's basically saying is it will diagonalize any system of equations. It'll diagonalize it for you. So it'll do that clearing out of the 0 underneath. Does that make sense? Echelon form is that diagonal echelon form. And row reduced means it's going to try and get it as cleaned up as possible. Now you have to be careful because there's another one. It's not RREF, it's REF, and that's just reduced echelon form, not reduced row echelon form. They're slightly different. So, all right, now pay attention, all right, because this is vital. I want you to look through here. I want you to look at your original system of equations, and I'm highlighting some numbers here. Those numbers are the coefficients. Coefficient is always the number in front of the variable, isn't it? This number is the coefficient in front of x. This is the coefficient in front of y. This is the coefficient in front of z. And this is the coefficient of the answer, or it is the answer, yes? So I have one row of numbers here in the order x, y, z, answer. The next row of numbers I have is what? 1, -3, 1 again, and then 10, yes? Then the next row is 5, -2, -3, and 8, yes? Okay. What we need to tell the calculator is that those are the 3 rows of numbers we have. It will return to us 3 new rows. And those 3 new rows will represent our answer. You'll see once we get it, all right? So how do I tell the calculator here are my 3 rows? Here's the first thing I do. I have to type in a bracket, not a brace, a bracket. And I think that's above the, I thought it was above the 7. Above your multiplication. You have to hit the, okay. The bracket says to the computer, here comes the rows, all right? It's basically saying, I'm about to start giving you rows. Now another bracket, which tells the calculator, here's the first row. So this first one's telling the calculator, start the rows. This one, first row. Now what you need to do is you need to type in the numbers across the first row with commas between them. So I'll type in what? 3, 3, 2, 4. All right? Good question. How do you put a comma? It's above the 7. Yeah. Everyone got that? Bracket which way? Like close bracket, right? Close bracket tells the calculator, done with the first row, right? Now I need to tell it, here comes the second row. So another bracket that starts my second row. And now I type in what numbers? 1, -3. Now what is it about the -3? When you type in -3, you cannot use the subtraction symbol, right? You have to use the negative. You understand there's a difference between the subtraction key and the negative key on the calculator. So -3, then, 1, 10. Then, close bracket. We done? No. Open bracket. Here comes the third row. 5, -2, -3, 8. Y'all still with me? Done with the third row, right? Now what do you think I need to do? Another bracket, which means I'm ending the rows, all right? And then a parenthesis to close the function to tell the computer, all right, I'm done. Like, I came in, I wanted to do a reduced row echelon form of a system of equations. Okay, here I'm going to start it out. Here's the first row. Here's the second row. Here's the last row. Okay, that's it. I'm done with rows. Now go ahead and close out the function and do the calculation. Hit enter. It automatically puts the parenthesis in the front. So when you type in enter, if it gives you like an error, go to something, you mess something up. Missed a comma, used the wrong negative. Anyone get it? I want to see what the answer looks like. Can I borrow your calculator? Now this is a fancy one. This is the plus. Let me see what yours looks like. Yours looks pretty good too. Let me see. Turn to me. Yeah, I can see that. Okay, so yours looks like his. All right, so yours is probably the fanciest out of all of them. So I'm gonna go with what theirs looks like, because yours is even cleaner. So the answers are looking like this. It's like a bracket, then what is it? 1, 0, 0, what? 2, then close bracket. Do you have it? Yeah. Oh, yours looks fancy too. And then you should see like another row somewhere. It says 0, 1, 0, -2. And then like another one says 0, 0, 1, 2. And then something like that. Do y'all see something like that? Can you look at your calculator and see that there? Okay. So let me ask you now to interpret this answer. What is this saying? It's saying that when you do the reduced row echelon form thing, right? When it does that, it turns your system of equations into this. So it's actually doing Gaussian elimination, but even further than we do in this class. So I want you to go back now and rewrite the system with x's, y's, and z's. What did these first row of numbers mean? That we had one what? 1x plus 0 y's plus 0 z's equals 2. Isn't that what that first row means? What does this next row mean? No x's plus 1 y plus 0 z's equals -2. And what does the last row mean? 0 x's plus 0 y's plus 1 z equals 2. In other words, x is 2, y is -2, and z is 2. Which is exactly what we got when we did all our work, right? So if there's not a solution, if there actually is not a solution? Yes. What would happen? No, it won't say no solution. That's a great question. It won't say error either. Here's what it'll do. This last one right here will say something like 0002. Okay, so what would that mean? 0002. No, it would say that 0 x's plus 0 y's plus 0 z's equals 2, which means 0 equals 2, which doesn't make any sense at all. So your calculator wouldn't prompt you with an error. It would give you a result that doesn't make sense. So that would be like parallel. So here, or you could have something else. Let's not get into it. Okay, look, what we're looking for then is a 1002, right? A 1 with zeros. Then we're looking for 0, 1, 0. Like, do you see this diagonal of 1s? See the diagonal of 1s? And then this right-hand side is basically x, y, z, isn't it? So that's pretty clean, isn't it? I mean, if you can type it in correctly, it's pretty fast. Now, I always get students in my calculus class that do it a different way, and they always tell me, hey, you know, this is the way I do it on my calculator, and they use the matrix menu, and they input the matrix, and I'm just telling you, there are other ways to do it, but this RREF function is on all the TI 83s and up. So if you upgrade to a different calculator, you can use this one. You know, it's been in the TI library of functions since they first, you know, had the fancy calculators. So that's the way I like to show it. Now, with this idea, there's theoretically, I mean, there's no limit to the size of system of equations we can do, right? Because this RREF did not say, hey, you can only do this with 3 equations, 3 variables. I could have had 5 equations, 5 variables. Could have had 10, 10. I would just have to go in and put in 10 rows, right? And then it would spit out the answer with 1s across. What's that? And you could do it for 2 equations, right? We stop using letters and we start using subscripts. So what we do is something like this. I write like 3x1 plus 4x2 plus 5x3 plus 6x4 plus 7x5 equals 10. And then I would have another equation, right? And see, with that, you never run out of variables. Yep, that's the way we did the polynomial coefficients in the general formula. Yes. Mm-hmm. Well, here's the issue. If I tell you you can use the calculator on the final to find the answer, you don't have to show me the work, then people who don't have it are going to feel like they need to go buy a calculator just for this. I don't want someone spending $100 on a calculator for one problem on the final or two problems on the final. You know what I'm saying? So I want everyone to do it by hand, but you can check your answer with that. Right? So this problem that I gave you right here, that we did by hand, you can expect that on the final. Something just like this. Not that exact problem. And I don't even think it'll be as bad as this, because here you have to do the 21 and negative 12. I think it'll keep it smaller. Okay? That seem reasonable? Okay. Now, yeah, oh yeah, you can get fractions, but I'm going to keep it clean. I mean, you could though. So let's. I think you understand kind of the idea, right, of how to do this? I mean, the system? Okay. I'll give you the option. Would you like to see another example of going through the whole thing, or are you ready to move on kind of to like the next thing? Move on? Move on? Okay. So 12.1.10. We did? So we're on 11? I thought the last one was 9. It was? Yeah, it was 9. Using the calculator to solve. Curve fitting. Some what? Oh. Okay. We're not talking about anything but math right now. So I want to show you something. I don't remember this. Remember, I was keeping track of my weight. I haven't been doing it. That's not a good example, but let me show you something in here. Let me bring a new file up. Let's say that I have some data on, I'm trying to think of some good data here. If I have one person, this is a number of people, if I have one person and I ask them to, what should we do? Let's do some physical activity like picking up trash or something, cleaning up. Okay, yeah, have you ever seen those crews out on the side of the road picking up trash, right? Okay, if I have one person doing that, it takes, let's say, 3 hours to, let's say, clean half an acre. All right, I'm just making this crap up right now, okay? If I have one person, it takes 3 hours. If I have two people, it actually takes 5 hours. Does that make sense? No? Yeah, we should go less. Well, now they're talking. They're not paying attention. They're okay. Okay, sorry. That doesn't make any sense. Yeah. Now, hey man, what'd you do last night? Okay, let's make it 1 hour. right? If I have 3 people, right, let's say it takes half an hour. Understand? Okay. Now, what I'd like to do is to try and fit a function on top of this data so that I can predict things that are happening, like what would happen if I had 4 people. Make sense? So I'm going to go to Excel here, and I'm going to type in that data. It was if I had 1 person, it was what? How many hours? 3. If I had 2 people, it was 1. And if I had 3 people, I put half, right? 0.5? Okay, so what I'm going to do is I'm going to just grab this. I'm going to highlight it. If you've never used Excel, don't worry. You're not going to have to use it on the test. And then I'm going to do what's called a scatter plot. Okay, so that's the plot, right? This is it. 1 hour. I mean, 1 person took 3 hours. 2 people took 1 hour. 3, half an hour. Yes? Now I'm going to click on that data. I'm going to right-click it, and I'm going to say Add Trendline. This is something that's built into Excel. And now what I can do is I can have Excel fit on top of this data. I can, oh, where'd it go? I can have it try and fit an exponential function to it. There, it just fit an exponential function to it. I can have it try and fit a line to it. I can have it try and do a logarithmic function to it, a polynomial function, a power function. I'm going to do a polynomial. I'm going to try an order 2 polynomial, which is a quadratic function, right? Order 2 is, highest power is 2. And I'm actually going to display the equation on the chart. And let me get this one out of here. So look, for that data, the data is like kind of jumping around. It's not smooth, right? But I can ask the computer to actually try and fit a parabola to it, right? Try and fit a parabola to it. And it fit the parabola, what, ax squared plus bx plus c, right? That's the parabola. It's y equals, our a is 0.75, our b is negative 4.25, and our c is 6.5. Make sense? How is the computer fitting that data? It's called curve fitting. That's what we're about to do. We're going to see how a computer would fit this data. You ready to do it? Good. I'm glad you're ready. So here's I'm going to write down our data points. Our data points are 1, 3, 2, 1, and 3.5 or 1/2. Yes? I would like us to fit a quadratic function to this. Why would we want to fit a function to data? Why would we want to do that? Yeah, I mean, like, if you only have 3 data points, you don't know what it would be like to have 5 guys out there, right? Or girls. There are girls that clean up side of the road too, right? So once you have a function, right, you could actually model what's happening and predict what would happen later. Yes? Predict it. If your function is a good fit, you should be able to talk about things that haven't happened yet. And so that's why there's value in fitting functions onto data. Okay, so let's fit a quadratic function onto this. What do all quadratic functions look like? Yes, but in terms of algebraically, like y equals ax squared plus bx plus c, right? That's every parabola out there looks like this. In order to actually pinpoint the specific parabola we're talking about, I actually have to know what A, B, and C are, don't I? Wait a minute. I need to know what things? A, B, and C. I need to know how many things? 3 things, right? I have three unknown things right now. Well, in order to figure out three unknowns, I'm going to need three equations. If I have three equations and three unknowns, I should be able to solve it, right? System of equations. So let's use the first point. What does the fact that we have the point 1, 3 mean? When we plug in x is 1, the y should be 3, right? So take this equation right here that we know our parabola looks like this, we just don't know what a, b, and c are. And let's replace x with 1, and let's replace y with 3. And let's see what we get. So we get 3 equals, if I replace this x with 1, what do I get? 1 times a, so just a, plus 1 times b, which is b, and then plus c. Everyone understand? Replace y with 3, x with 1, you get this. Well, what we have here is a linear equation, right, with 3 variables. I have 1 equation so far. Where am I going to get the other ones? The other 2 points, right? So now let's replace x with what? 2 and y with 1, and let's see what happens. So using the point 2, 1 for x and y into that same equation up there, we get 1 equals, replace the x up here with 2 now, 4a plus 2b plus c. There's my second equation. Two is going in for x right here. So 2 squared is 4. 4 times a is 4a. Got it?
It's like distributing, right? It's not a exponent. The answer of x. So you know you do x squared?
Yes.
You have obviously put it there. And it's going to be in front of the variable. It's not an exponent, right?
That's right. It's in front. Because it's multiplication, it's a times 4, but we usually don't write a times 4. We write 4a. What about the last one? What are we going to plug in for x? We're going to plug in 3 for x and 1/2 for y. So that means what should y be? 1/2. So 1/2 should equal 9a plus 3b plus c. There's my third equation. I have 3 equations. I have 3 unknown variables. I have a system of equations. I have enough information to figure out what a, b, and c are. Right? So I should be able now to create a system of equations. And let's just write these in the proper order. A plus b plus c is 3. So it's kind of like we had x, y, z equals a number. I'm just rearranging this, putting the number on the other side. 4a plus 2b plus c equals 1. And then finally, 9a plus 3b plus c equals 1/2. You all with me? Now, for those of us who have the calculator, let's use RREF. Because I don't want to go through this whole thing by hand trying to wipe out the, things. Nope, you're going to do RREF, bracket, bracket. What are the coefficients? You have to find the coefficients of these variables. See, we're using ABC instead of X, Y, Z. So what are the numbers on the first row? 1, 1, 1, 3. 1, 1, 1, 3. What are the coefficients of the second row? 4, 2, 1, 1. Next row, 9, 3, 1, 1/2. So 1, 1, 1, 3.
So like in the test, we are going to have to show work.
Yes.
And we're not going to be allowed to go like...
Well, that's what I was saying. I think you stepped out when I was saying it. You can check your answer on it, but not everyone has it. If everyone, by the time of the final, has a calculator, borrows one from a friend who has this, I'll let you use it on the test, and that'll be all you have to do. But we have to have everyone have one, or everyone have the ability to do it. But I don't want anyone spending $100 just for that, you know? What did you get?
0.75, negative 4.24, 25, and 6.5.
Okay, yeah, so you should be getting something that looks something like 100.75. Then, and then, you may have more brackets here depending on your calculator, but that's what happens after the REF. Always check, do you have 1, 0, 0, then a number? Yes. Do you have zeros and then a 1 in the middle? Yes. Do you have zeros and a 1 right here on the second to last number? Yes. So this is that diagonal I was talking about. We have it. And so these three numbers are our answers for what? A, B, and C, right? A, B, C. No, because in this problem it was A, B, C that we were solving for, right? A, B, C. So the original function, what we have here is A is 0.75, B is negative 4.25, and C is 6.5, which means that our function, our quadratic, is y equals ax squared plus bx plus c. We didn't know what A, B, and C were, right? We didn't know, but now we do. 0.75, go back to the original, replace A, B, and C with what you just got. This should be the parabola that fits that data. That's it. We found the function. We have fit a quadratic function onto our data. Yes? Which, going back to Excel, is exactly what Excel got. Right? Yes.
I was going to ask, I think I stepped out too. Can you explain the diagonal, like the answers for A, B, and C? Is it just add the B to the final product and C to the final product?
I'm not sure I get it. And I'm not sure I get your...
I don't understand how you got that.
The calculator did this and spit this out. What I'm trying to say is just make sure that your calculator is giving you 1, 0, 0, then 0, 1, 0, and then 0, 0, 1. That would mean that A is this, right? Because this kills off B and C. This would mean that A is gone, C is gone, so this means B is this. This means A and B are gone, which means C is this. That's the problem. There can be a system, I won't give you one, but moving on in more math, if this last one right here was a 0, then what you'd be saying is that 0, the whole left side is 0, equals 6.5, which 0 cannot be 6.5, which means that these planes don't hit each other. It's an inconsistent system is what they call it, an inconsistent system of equations. That's how you would know, but you have to pay attention to that. Then you would get something like 0, 0, 0, 0, 0, which means 0 equals 0, which is always true. You could get, well, no, they'll always divide out and make it 1. It'll always be 1s or 0s. 0 equals 0 is all solutions. Like that would be like where they hit each other in that line in the book. Or you could have a plane on top of a plane on top of a plane, all the same sheet of paper. You would get 2 of them. Yeah, you get 2 of them to be. But again, this is beyond what we're going for. Yeah. Yeah, no, I understand. It's a good question. Okay, any questions? Any issues? We're going to do one last thing today, and then I'm going to cut you loose. I don't remember. I thought I put it up here, didn't I? Last class? I wrote everything out about the final last class. Yeah, yeah. So Tuesday, from 11 to 1:45. Not next week, the week after. Yeah. Yeah, we're going to have time. I think Tuesday we'll start reviewing. Yeah. Yeah, review your tests. Yep. So I would, over the weekend, try and spend a little time going over the tests, the things that you had trouble with. That way we can start talking about those issues next week. I think there might be a little bit more I might throw in here, but not much. It'll be minimal.
How many topics do we have left? This one and what else?
Well, I'm kind of blending these last sections together and just pulling the things that I think are important out. Okay. Yes, this is the last thing I'm going to do today. What does that say? Matrices. Matrices. Or you've heard Matrix. You've seen the Matrix before? Old school. Keanu Reeves, slow-mo, back when that was like the best animation ever, right? That was like groundbreaking special effects ever, yeah. So, unfortunately, the Matrix movie is not the same as what we're going to be talking about here. The only similarity they have is that there's a bunch of numbers, and we've got a bunch of numbers also, all right? So check this out. We take something like this. And we call that a system of equations, right? We call that a system of equations. We use the brace on the left to let you know we're trying to find the solution to both equations, something that solves both of them at the same time. Well, because the x, y is kind of understood to be our variables, right? Our x and our y. I should start this over. If we line this up so that the x's are always the first thing, then the y, then there's an equal, then there's a number, right? So x's are lined up, then y's, then a number. Then we don't really need to write x, y in the equal sign because we understand they're there. So what we could do is rewrite this system in a different notation where we use a big bracket and we just list out the coefficients. Now, because there is an equal sign in here, you'll see the book use a line down here like this, just like that. Some books use dotted lines like this. It just depends. For us, we'll use a straight line because the book does. So that kind of tells you where your equals is. So just understand, this right here is being rewritten like this. 2 is the coefficient on x, 1 is the coefficient on y, equals 10. Negative x plus 2y equals 7. Understand? It's just a different notation. This is called an augmented matrix. Hold on, give me just a second. The reason we call it an augmented matrix as opposed to just a matrix is the fact that it includes the equal signs. All right? I could also write just this, and it would not be an augmented matrix. 2, 1, negative 1, 2. And that would be what we call the coefficient matrix. That's just this side, isn't it? This would just be a matrix. Might call it the coefficient matrix. They're not the same. Okay? The augmented matrix includes your last column of numbers includes the right side of the equation, the equals part, right? It's including this. The left side, the left of this line, I could write that as a matrix by itself, and that would be what we call our coefficient matrix. It's the coefficients of our variables, right? Understand? This is just notation. Now, when we look at a matrix, it doesn't matter what the numbers are, how many numbers we have across and down. We have some terminology that we want to understand. So in general, if I have a matrix, and let's call this A11, A12, A13, and this goes on. Let's say A1M. And now the matrix goes down, A21, A22, A23, dot, 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 A2M. Now just follow me for a second, okay? Then this goes down until I get to A-N1, A-N2, A-N3, all the way till I get to A-N-M. I know that looks weird, but it's really not as bad as it looks. There's an A, which represents the fact that this is a number. Okay, this is a number. The first number you see here, this is not 11, this is not 12, this is not 13. What this means is the first number is the what? The row you're in. The second number is the column that you were in. Okay? So A23 is the number that's in the second row, third column. Make sense? What would A47 be? The number in the fourth row, seventh column. ANM is the number in the nth row, mth column. So how many rows do I have here? 1, 2, 3, 4, till I get to what? N. How many columns? 1, 2, 3, 4, 5, 6, until I get to M, right? This is N rows, M columns. Yes? N rows, M columns. This is N rows, M columns. M and N? Uh-huh. So this would be, what we call this right here, would be called an N by M matrix. An N by M matrix. That's an N by M matrix. Now, what you always need to remember here is that this is always the rows, this is always the columns. So if I have a 3 by 5 matrix, it's 3 rows, 5 columns. Now the way that I've remembered that, has anyone ever heard of that soda called RC Cola? RC Cola, rows, columns, rows, columns, rows, columns. So when you see that number, RC Cola is what I think of, so I can remember rows, columns. So what is this matrix right here? It's a what by what matrix? 2 by 2. This is a 2 by 2 matrix, isn't it? 2 rows, 2 columns. What this augmented matrix is a what? 2 by 3 matrix, isn't it? What would a 3 by 1 matrix look like? 3 numbers straight down, right? 3 numbers straight down would be a 3 by 1 matrix. You following? Okay. Now, let's look at some. That was note 1, I guess. I may have not put note 1. Let's look at some matrix operations. I'm going to call it matrix ops. Let's start with addition. What if I give you this matrix and ask you to add it to this matrix? Do you think you can add those together? Okay, both of these matrices are what by what's? 3 by 2 matrix, 3 by 2 matrix, right? Those are both 3 by 2s, aren't they? You can only add matrices together if they have the same dimension. In other words, they have the same rows and columns. And then what you do is you just add them element by element together. So I'm going to take the first row, first column, add it to the first row, first column here. And what do I get? 7. Then I go and I do the first row, second column to the first row, second column, and I get 1. Right? And just add through? Yes? Understand? So what, since these are the same rows and columns, I can add them. But I just do like top left, added to top left here. Top right, added to top right here. And you can also use your calculator to do it. All right, so what would the rest of this be? 4, 6, 3, and then 7. There's your matrix addition. Pretty simple, right? I mean, there's not a whole lot here. You add 2 matrices together, you're done. How about subtraction? Same way. So I'm going to just say /subtraction. If I do subtraction, I would have put a minus sign here. Then it would have been what instead? 3 minus 4, which is -1. Then it would have been 2 minus -1, which would have been 3, and so on and so forth. Do you think you can handle that? Yes? Okay. Here's where things get tricky. Multiplication. Matrix multiplication is a little bit more involved. What you would hope it would would just be that if I multiply these two, right, instead of add, that is go 3 times 4 is 12. 2 times -1 is -2, right? I mean, that's what you would hope for, just multiply. That's not the way matrix multiplication works, unfortunately. So here's what we have to deal with matrix multiplication. If I have a matrix, which I'll call A, and I want to multiply it with the matrix B, all right? So here A and B, I'm using capital A and B, are matrices. Okay? Notice my use of capital A and capital B. That is standard notation for matrices. If I want to multiply these 2 matrices together, I need columns of A to be equal to rows of B. That must be true in order for me to even be able to do it. So let me give you an example. Let's take 2, 1, 4, 6, and multiply it times 2, 5. Can I do this? What's rows, columns here? What's RC cola here? This is a 2 by 2. What is the rows, columns here? Rows, columns, 2 by 1, right? Rows, columns. You need the columns of A, that's this, to be equal to the rows of B, that's this, right? You need those two to be the same. So yes, they are the same. We should be able to multiply them. You can't do it. It's not possible. Exactly. That's the next question, right? So, are you doing it on your calculator? Yeah, do it, because I want us to see the answer first, and then I want us to try and extrapolate where it comes from.
I'm doing the first one.
Okay. 938. The answer to this is 938. Whoa. Okay, so let's just notice, first of all, if I'm trying to multiply two matrices, I have to have the columns here match the rows here, which it did, right? And my answer became a what? According to the calculator, my answer is going to be a what? What's the dimension of this answer? 2 by 1. Well, guess where that 2 by 1 comes from? The outside ones. In other words, if I had done a 3 by 2 with a 2 by 1, my answer would be a what? 3 by 1. If I had done a 3 by 2 with a 2 by 4, my answer would have been a 3 by 4 matrix. Yeah? Okay. Where the hell is 928 coming from? 938 coming from? Let's see if we can figure out where 9 comes from. Where does 9 come from? No? Okay, let me try and help you here. What if I take this 2 and multiply by this 2? What do I get? 4. Hold on to that. Add to it this times this, and what do you get? 9. Add those two together. Oh, sorry, you already did. Right? 4 plus 5 was 9. Yes? Now, I'm going to go through this again, but let's just try to get you to see it. What was that number? 2? Okay. Then, to get this bottom number, what do I do? 4 times 2 is 8, plus 6 times 5, which is 30. So 38. So what am I doing here? Yeah. Yeah, it's you're doing row 1 times column 1. Okay, so back up here. How do I get this number? This number is in what position? It's in the what row? First row. Which column? First column. This one is in the second row, first column, right? So if I want to get the answer for the first row, first column, I have to multiply the first row times the first column. If I want to find the answer for the second row, first column, I have to multiply the second row with the first column. I know it seems weird, but there's algorithms. You can just memorize formulas in the book, but I think it's more useful if you understand like the pattern of what's happening. So let me try this. I want A11, so I want to take row 1 and multiply it times column 1. Because it has 1, 1, right? Row 1, column 1. So let's take row 1. I'm just going to write it down over here. Row 1 is 2, 1. And I'm going to multiply it times column 1, which is 2, 5. Do you understand what I'm doing here? Row 1 here is multiplied times column. The way we do this multiplication, when you do a row times a column, is you just do first one plus second one, and add them together, right? So 2 times 2 plus 1 times 5. Yeah? That's 9. And that's where that came from. Got it? Next one. I'm going to do row 2 times column 1. So row 2 is 4, 6 times column 1, which is 2, 5. And then do the same thing. 4 times 2 plus 6 times 5, which is 38. Understand? Okay, let's try something harder. I mean, more complicated.
I'm not sure what we're getting out of doing this.
I understand. I understand. I can give you a general picture of what's happening, all right? You want to see a preview? Okay, just a real quick preview. Okay, if I write this down, everyone, 4 times x equals 8, what's the answer? X is 2. So what you did is you really multiplied both sides by 1/4, didn't you? I mean, you divided by 4. Same thing? Multiplied by the reciprocal? And you got x was equal to 2. Yes? Okay, when we have a system of equations, 2x plus 3y plus z, and then another equation, right, equals 10, 5, let's say 2. What I'm going to be able to do is I'm going to be able to rewrite this as (10, 5, 2). My coefficient matrix over here, whatever numbers there are here, and this is going to be x, y, z. And so what I have is a 3 by 3 system or matrix multiplied times a 3 by 1 matrix. The result of that is a 3 by 1 answer. So the way that I could get to this answer of what x, y, and z are is to actually multiply both sides of this equation by whatever the hell the opposite of this is, which is called the inverse matrix. So this matrix right here is actually the 4, and then we have to come in on both sides with something, but the question is, what's the inverse that undoes this matrix? Does this help a little bit? But we have to still know what it means to multiply matrices together, like how you do it. You asked, I answer, sorry. Okay, so let's try this one, this example. I would like for us to multiply, let's do 2, 5, negative 1, 6, 0, 3. Can I multiply those two? Can I do it? Yes? Okay, what's the dimension on the first matrix? 3 rows, 2 columns. What's the dimension on the second one? 2 by 3. So it's possible because these two match, don't they? My answer is going to be a what? A 3 by 3 because it's this and this, right? The outside ones is the result. So my answer is going to be a 3 by 3. Y'all still with me or not? So if it's a 3 by 3, then I'm going to have an A11, an A12, an A13. I'm going to have an A21, A22, A23. I'm going to have an A31, A32, A33. Oh, I have 9 answers to get here. No big deal. Right? I have to fill those 9 spots in. RC Cola, right? RC Cola. Row, column, row, column. First row, first column, first row, second column, first row, third column. Second row, first column, second row, second column, second row, third column. Third row first, third row second. Yes? Understand? Okay, so how are we going to get each one of these, right? Okay, so let's try and get A11. How do I get A11? A11 I get by taking row 1 and multiplying it times column 1, right? Where's row 1 from the first matrix? 2, 5. I'm going to take 2, 5, and I'm going to multiply it times what? The first column of this matrix. 5, 2. Not divided. 5, 2. Understand? I'm taking the first row here, multiplying times the first column here. Now, how do you do this? 2 times 5 plus 5 times 2, which is 20. 8 more to go. How do I get A12? Well, I'm going to take the first row and multiply it times the second column this time, right? So this is going to be 2, 5 times what? 2, negative 1, which is 2 times 2 plus 5 times negative 1, which is negative 1. I know I'm moving quick here, but are y'all following the pattern here? I don't know why I put a comma there. What comma? I never saw a comma. Thank you. And I keep going. So let me pick one of these. I'd go to this one now. Let me just pick one of these. How about A32? How would you find A32? I would take the third row of the first one times the second row of column of the second column of the second matrix. So what's row 3? 0, 3. I'm going to multiply that times 2, negative 1, which is the same as 0 times 2 plus 3 times negative 1, which gives you negative 3. Did you already do all this on your calculator yet?
Not yet.
All right. So far, I have, what, a 20 here, a negative 1 here, right? I shouldn't do that. So far, my answer is this. 20, negative 1, and then we did A32, which was negative 3. We did all those by hand, right? Yep. But if you do the rest, which I won't do, you'll get 17, 7, negative 8, 17, 9, and 6. Understand? All right, so what should you do for homework? Nothing. No. Yeah, and has anyone watched The Usual Suspects yet? You watched it? Had it been a while, or you'd seen it before, right?
I think I caught a couple glimpses of it, but I never watched it.
Did you like it? I mean, honestly. No?
It was mildly entertaining. I didn't really like it.
Okay.
It's okay.
Okay.
I like the character. Is that like one of your favorite?
No. It's just every time I talk about flipping something, I think of the scene when he's being interviewed, interrogated by the cops, and he's like real cocky, and he's like, "I'll flip you." You remember? You know what I'm talking about? Yeah, Del Toro. That guy. Yeah, he's funny in that movie. So every time I think of like flipping fraction or something, I always think of him in that scene. I'm flipping. Yeah, I'll flip you. Yeah. Yes. How do you do what? You have to enter the matrices. I mean, I have to show you. You could do this. You could do bracket, bracket, row, just like we did with the RREF. Like this would represent a matrix with 2 rows. Like if you did That would represent this matrix. Okay, you type it in your calculator like that, and then you say times, then you put another one over here, and you do the same thing, and then it would multiply the two together. I can show you, just not during class. So here's what I want you to do for homework. All right, I'm going to just give you a homework assignment. Some of it's out of the book, some of it's not. Where are these pages? Okay, I want you to do page 855. I already gave you some homework out of this section, right? Okay, so I want you to do 51 and 52. Trying to avoid fractions. Also do 49. All of those answers, we will avoid fractions. Okay, you're going to get nice integer answers. You're going to have a point. They're not going to be inconsistent where they don't intersect. So that way you're just getting the practice of going through. Don't just type in your calculator and say, got it. You know, I mean, go through that thing of trying to get zeros underneath. And then what I'd like for you to do for homework also is I'd like for you to multiply by hand Can you multiply those? Yes, okay. If you can get that multiplied out, you'll be good. Like that means you understand how you're supposed to line everything up. All right. Adios. Get out of here.